Hey everyone, and welcome to a new episode of Dev with Serdar. And in this episode, we're going to be taking a look at doing GPU-accelerated math with CuPy and Numba in Python. First, some introductions. CuPy is a variant of NumPy, the high-speed Python math library. And CuPy uses the GPU for accelerated and massively parallel computing. It's a drop-in replacement for NumPy for the most part, so most of the work done with NumPy can get a significant speed-up with CuPy. Numba I've talked about before in a previous video. It's a JIT compiler for Python. You can take functions that work primarily with numerical values or arrays and compile them to assembly, so they run at high speed. It also has the ability to deploy that compiled code to GPUs, where it can run in parallel using CUDA, one of the industry standard frameworks for GPU computation. This is a part of Numba I haven't explored before, so I'm going to examine it in greater detail through this video. So what I have here is a demonstration program that uses CuPy and Numba's CUDA hand in hand. It searches for all prime numbers from 1 to a given value using the primitive but effective sieve of Eratosthenes method. It also does as much of this work as possible in parallel on the GPU, so it's much faster than a naive implementation that just tries to process the whole range of numbers in sequence. Let's start with the sieve primes function. This is where we kick off the whole process. The first thing we're going to do here is take the range of numbers we're going to process and use that to figure out how many blocks to divide that up into. Each of these blocks is a unit of work that is going to get processed separately on the GPU. And then next we create an array in CuPy to hold our primes, and we initialize its values. The process for doing this is syntactically the same as with NumPy. We have a method called full. We give it the size of the array, the value to fill with, and the data type. So this creates an array of all ones with the first two elements set to 0. Now, just about all of the CuPy methods that you would deal with on a daily basis are clones of NumPy methods. What's different is that the data is created and processed on the GPU to speed up processing, and also to reduce the number of transfers from main memory to GPU memory. We get back everything from the GPU only when we're completely finished. This is important because the more times you bounce back and forth from main memory to GPU memory, the more overhead you're going to introduce into the whole operation, and the less you'll see of any actual speed up. I'm going to go into this in greater detail later. So for now, we're going to actually start using GPU-powered operations in Numba to do the real heavy lifting. So first we have this context manager. This ensures that anything that we are creating inside this block doesn't get deallocated from the GPU until we're done with it, so that parallel operations can complete properly. This is basically housekeeping. Next, we have this function call to this function sieve forward. That's the core of our actual prime search work. This function we wrote in Python and then wrapped with Numba's CUDA JIT system, so this function runs on the GPU. Now you'll notice that the wrapper we have here, this decorator, this lets us describe a function signature that will be used for when the function is compiled. So in this case, we're saying this function takes in an array of unsigned integers and also a single integer. So that represents a segment of the array that we're working on and the size or the bound of that array. So when we compile and run this function, we're not just running one instance of it. We're running a whole slew of them in parallel. Each one of them is given a slice of the array to work on separately. So inside the function, we have this method CUDA.grid, which obtains the starting position in the array for each instance of the function. So we use that, along with everything else that we've been passed, to perform the actual sieve calculations on the array. Now when we call this wrapped function down here, you'll notice we have this peculiar syntax for it. This is something that is a product of using the CUDA JIT function. We have this function's name, and then we have these square brackets, and in these square brackets we supply the number of blocks that we're processing, and the size of each block. This is all stuff that we have to supply for the sake of the parallelization on the GPU. And then after that, we have our actual function call arguments. We have the array of primes and the bound for each segment of the array that we're processing. So we make this call, and it dispatches to the GPU this whole slew of parallel instances of our function, and then waits for all of them to finish up. And then for the last step, we take the array that we've been computing, and we return a version of it without the zeros, just nothing but the prime numbers that are left over. Now let's run this code and see what we get. So when we first run this code, you'll notice that there is a significant delay. That is because we have to instantiate the JIT compiler and do a number of other setup operations. This is something that I mentioned in my original discussion of Numba. There's a certain amount of warm-up time, and the code has to actually be compiled in order for it to be executed for the first time. That's also why we have this cache equals true line in the decorator for the JIT. It allows us to reuse the compiled code across various runs to make this initial startup time a little bit less burdensome. But despite the initial delay, the total time that it takes to find the first 100 million primes is around a couple thousandths of a second, and that's with a method of prime search that's not known for being particularly fast. This blocks number, by the way, is how many subdivisions that we're using for this job, as we computed at the beginning of the main function. So you'll notice that if we rerun this code, the initial startup time is now much lower, now that many of the things that needed to be warmed up are in fact warmed up. So again, what makes GPU-based computing so powerful is that we can take many operations and run them in a massively parallel way. So for the sake of comparison, I'm going to run another version of this code, which only uses the CPU to do its work and has no parallelization at all, just to give you an idea of how dramatic the difference is. Now, the amount of parallelization that you're going to get depends on a number of things. One of the biggest is the number of CUDA cores that you have on your GPU. I'm running this on a GPU with 1,408 CUDA cores. It's a GeForce GTX 1660. It's not the most bleeding edge hardware out there. But the mere act of making these operations parallel and at the kind of scale that we can't have with a GPU at all is a huge boon. Now, as you can see, this non-parallel CPU-only code for computing 100 million primes, that took 14 seconds, plus or minus. But our GPU-based, massively parallel version, again, a fraction of a second. Also, going back and forth from the GPU to the main system constitutes a bottleneck, as I mentioned earlier. You'll notice that we have this second number here, result delivery time. That's how long it took to compile the results into an array and return it to the system from the GPU. That took almost 2 seconds by itself. In fact, that's where we're spending the vast majority of our time with this program. So a possible future route to optimization would be to find better ways to deal with that issue. Still, even with that bottleneck, we're getting results far faster than with a conventional CPU non-parallel version of the same problem. So to sum up, CuPy gives you GPU-accelerated versions of the functions available in NumPy, performs all its work on the GPU. And you can use that hand-in-hand with Numba's CUDA JIT to write functions that also run on the GPU. This lets you take problems that lend themselves to being massively parallelized and chew through them on the GPU. And while there still may be some performance overhead incurred by going back and forth from the GPU to the rest of the system, you can minimize that. And the performance gains for doing the work on the GPU are enormous. So that's it for this video. If you liked it, please leave a comment below. Don't forget to subscribe to Dev with Serdar. And if you'd like to see more of my content, please follow me on Facebook, YouTube, and InfoWorld.com.